So what I can do is I can take this revenue function right here and I can plug it into my calculator. I've got it plugged in here. You see there's the X beside the 26,000. Just went down to the next line. And I can graph that. Now I'm going to hit zoom 6 to graph it initially, so make sure it's in the same window that you guys see. And there, you can see there's nothing there. It looks like, anyway, there's nothing there. If I hit trace, remember trace puts a cursor on the actual function. So you see 0 zeros on the function, which makes sense because both terms have an X. But if I just move my decimal just barely a little bit off the origin, you see 0.212, and the Y value is huge. It's like way off the screen. Remember, the top of the screen in the standard window is Y equals 10, and we're talking about 5,500. So it's there. It's just going off the screen. It's so steep. Okay. Now, what a lot of people do here is they just start playing around. They press trace and they start looking for the biggest value, and they don't take the time to think about it, or they'll go to their table and they'll start scrolling and they'll start looking for the biggest value in this column, and they don't take the time to think about what's in control here. Alright, this is the function that helped determine this. All we did is multiply this function by X. So this function right here is kind of at the heart of everything. So what I'm trying to get you to see here is this function right here has a domain. Right? The number of passengers can't be a negative number. Okay, it can't be a negative number. So what we can do is set this thing equal to 0. So 26,000 minus 100x equal to 0. Which gives me 26,000 equals 100x, and then I divide both sides by 100. So x equals 260. Okay, we can't set that price really above $260. We're paying $200 now. If we set it above $260, what this is saying is we're not going to get any passengers. If we set it any more than that, we're going to have a negative number of passengers. Alright? So the domain of this thing is 0 is less than x, less than or equal to 260. Because, again, we could set the price to 0. That would be kind of silly. I mean, you know, that's saying that we would have 26,000 passengers. If we gave away flights, that would probably be, you know, every flight full. But if we charged $260, we would have no passengers. So this is like max capacity, I would assume, all the way up to an empty airplane for each flight. So that's our domain. So there's no point in looking anything beyond these two. Okay. Now, and if you also think about what our revenue function is, it's a quadratic, it's a square, and it's got that negative number starting off. So you end up with something that looks like this. It opens downward, it has a peak. And because parabolas are, they peak in the center, then more than likely right here in the center of these two numbers, which would be 130, is where this max takes place. So if you go back to your graph, again we can't see anything, but if you extend your window initially, make your x minimum 0 because of the domain, make your x maximum 260. Alright, and let's go up in 130s so we can see where that 130 number is. Let's graph that initially just so we can see right there's the 130. Okay. Now what we want to do is press trace, type in 130, that number in the middle. There's 1,690,000. So let's make our window go from 0 to, instead of 1,690,000, let's make it 2 million. Right, and we'll go up in 500,000s. Now when we graph it, we see a nice arcing parabola, and there's our peak, like we were saying right there in the middle, right around 130. And in fact, there is a feature on your calculator, second trace right there, maximum, that will show you what this maximum is. Okay, you need to go to the left of where you think the peak is. You need to go to the right of where you think the peak is, and then best guess of what the peak is. It runs through its little algorithm, and there's our peak. Okay, it's got that decimal to it because it literally is a computer algorithm, but it is taking place at 130, like we were saying, right there in the middle of this parabola. All right, now that's heading towards calculators, and actually an easier way to find those maxes and mins when you get to calculus, rather than having to have your calculator find it for you. That you'll do when and if you guys ever take calculus. But I just want you to know that that's why we would study that. That's why a business would model something like this, keep data, and realize that this is what's happening. And then once they realize that that's what's happening, they can make their model and determine what price to set. Once I have that maximum, this is the price I would set tickets to be to maximize revenue, as much money that I can make. Alright, so another question, another very common type of question that you see here is you got a piece of metal, and what I'm going to do with this piece of metal is I'm going to cut out corners, okay, and when I cut these corners out, I have this like, cross-shaped thing, and I'll fold up the edges right here. Right, these corners will then be gone, and I'll have something, that just kind of looks like this. All right, and then I'll just fold along these edges right here, fold them up, and I'll get something that kind of looks like a box. All right, and what we're wanting to do is come up with the volume of the box. How much stuff can I put into this box? And it's going to be a function of how much did I cut off. How big of a chunk did I cut off of this thing? So, if you think about it, the smaller the corner that I cut off of these things, like if I cut off a teeny tiny corner like this out of each section, I'll have this box that has a really huge base, a really big base, but it's just not very tall. It's just a teeny tiny width right there. But if I cut off a bunch from each corner, then what I end up with is this really tall box, but it's not very wide at all, something like that. All right, so what we're trying to do here, what you would try to do in calculus, is to come up with what would be the ideal size square to cut off of each corner to maximize how much volume this box can hold. All right, so we're told that this original box is 12 inches on each side, 12 by 12. And we're trying to come up with what length right here are we going to cut out from this original square on each corner to maximize this volume. All right, now think about this thing once it's folded up, what it's going to look like. Okay, so this is what's being folded up. These sides right here are being folded up. And when they do get folded up, they were down here, and they're getting folded up, and they're determining these heights. So since these pieces right here, this length right here is X, this length right here is X, okay, these are determining this height right here. So this piece right here is x. Now, this length right here is this original length from here to here, right, which was 12 inches. And then we're taking off an x on each corner. One x on the left side, and then another x on the right side. And the same thing up and down. Okay, this was originally 12. Alright, but we're taking off those two x's. So this dimension here is 12 minus 2x, okay? X minus x. Minus x minus x is minus 2x. And so therefore this dimension over here also is that same thing. 12 minus 2x. Alright, I got it written in black over here. Alright, so that's what all of these sides look like. X, 12 minus 2x, 12 minus 2x. Now, if you remember the volume formula for a box, volume is just length times width times height. So length, width, height. So the volume here is length times width, which is 12 minus 2x times 12 minus 2x, which I can write as 12 minus 2x squared, times the height, which is x. So there's our volume formula. And we could plug in anything in there as long as it doesn't make a negative volume. Remember, volume can't be negative. Alright, so this right here, this part is saying, alright, we just need positive values, so x is greater than 0. And then this right here can't be negative either. Okay, so 12 minus 2x squared, that has to be greater than 0 basically. Alright, take the square root of both sides, you just get 12 minus 2x is greater than 0. And then if you subtract 12 from both sides, you end up with minus 2x is greater than negative 12. Okay, I'm just subtracting 12 here, subtracting 12 here. So I left with minus 2x on the left, greater than negative 12 on the right. Alright, divide both sides by negative 2. And I get x is, this is a 6 over here, but this will have to be flipped from greater than to less than. Okay, so remember this part right here, for it to be positive, this part would have to be positive, greater than 0. And then this part is saying we have to be less than 6. Okay, so x then has to be between 0 and 6 for this to have any type of value. So in interval notation, 0 to 6, because we can't not cut off anything because we wouldn't have a box. And then if we cut off 6, think about it. If I cut off 6, this is 12. If I cut off 6, that would be 6 gone this way, 6 gone this way, 6 gone that. What I would end up with is, instead of one square with the corners cut out I could fold up, I'd end up with 4 little squares, and I wouldn't have any anything that I could then fold up and make a box out of. So that's why we don't include the endpoints here. Okay, we don't include 0 because we got to cut something to be able to fold something up to make a box, and we don't include 6 because that would go all the way to the middle, and then we wouldn't have anything left to fold. Excuse me. Another common example, the making a fence type problem. Let's just draw a rectangle. It doesn't matter what it looks like. Alright, so we got this rectangle. It says we have 140 yards of fencing to enclose this rectangular garden. Alright, express the area of the garden A as a function of one of its dimensions x. So remember, area equals length times width. Okay, so if one of its dimensions, let's say this down here, the length, is x, that means this is also x. Okay, so the width, these other two sides, we don't know what they are yet. But what we do know is that whatever they are, they have 140 yards to go all the way around. So I do know right now that two W's, both of these W's here, 1, 2, plus the 2x's is equal to 140, the total amount of yards we have to work with. Alright, now if I solve for w, meaning I subtract this 2x over, I get 2w equals 140 minus 2x. Now I've divided both sides by 2. Alright, and remember, when you divide a sum or difference by 2 or any number, you have to divide each part. So 140 divided by 2 is 70. 2x divided by 2 is just x. So w equals 70 minus x. Now, why is that important? Because area equals length times width. The length we said is x, and w we just found to be 70 minus x. Right? So what we end up with here is a function, area, the function of x, is equal to x times 70 minus x. And again, we would distribute to simplify this. So x times 70 is 70x, minus x times x is x squared. So there's our area function as in terms of one of its sides, x. Okay. Now it's important when you do go through this process that when you have two variables and you're wanting to express the function in terms of one of its dimensions, okay, that you solve for the other variable. Alright, I want it in terms of x. I have w in x, so I solve for w. Alright, why do I do that? Because when I plug into this other formula, since I have w isolated, I'll bring in the other variable in there. And now there's only one variable in the expression, and it's the one that they want me to use. Okay, so if you're told specifically, use x, and you bring in another variable, or you have another variable in the formula, get an expression that solve for the other variable, so you can plug in and only have one in your expression. Alright, this is very similar to the last one. It's just a different shape. It's not a rectangle, it's a cylinder. So what we're trying to do is express the surface area. Alright, this is the formula for surface area. Alright, in terms of the radius. So r, and only r. Okay, now notice, the problem here, not pi, pi is a constant. The problem here is this h. We want that h out of there, because everything else is r. So what we need to come up with is a way to get h out of this. Okay, well, they give us the volume, 22 cubic inches. And because it's a right cylinder, the volume of a right cylinder is the area of the circular base, which is pi r squared, times the height. So that's the volume of this thing. So the volume is pi r squared times h, and that equals 22. Okay, now what are we trying to do? We're trying to get this equation down here to not have any h's in it. So I take another formula, another value that relates r to h in some way, and since they give me volume, I'm going to use the volume formula, and I'm going to solve it for h so I can sub it out of here. So I'm going to solve for h by dividing by pi r squared. That'll get h isolated. So h equals 22 over pi r squared. And then I'm going to substitute this h right here in the area formula. Two pi r times, there's the h. I'm going to replace it with 22 over pi r squared. Okay, and the only thing that's going to happen here is this pi and this pi is going to cancel. And this r is going to cancel with one of those r's, leaving with just a regular r. And then the 2 and the 22 will multiply together to give me a 44. So I get area as a function of r, so a with the r in the parentheses equals 2 pi r squared plus 2 times 22 is 44 over r. Right, and there's my function. How do I get area in terms of just r? And once again, if you're thinking, where does this go? Where do I go next with this? The company that makes this soda can, or makes this soda, they have to pay for how much, for the amount of material they use to make the can, or the amount of material they use to make this can is its surface area. So if I wanted to minimize surface area with a fixed volume, then I would take this function and determine, because r is the only variable, I could determine what radius would minimize the volume. So minimize the surface area. So I could plug that into my calculator. It would be much more funky looking, but I could plug that into my calculator and get a graph and see the minimum point, the low point.